Hi everyone, we continue working with our database tool. Last time we started looking at table creation and I decided to add automatic table creation as a starting point. And I came up with the idea of connecting a real instrument. Here I'm holding an USB-6008. Let me remind you, this is a multifunction data acquisition DAQ device. It provides analog inputs and outputs as well as digital inputs and output channels. And we connected our photosensor to its analog input. In the previous episode, we created a virtual object that communicates with this real-world system. That means when the light changes, when more light reaches the photosensor or less light reaches the photosensor, the voltage changes accordingly. This voltage is fed into the analog input of our USB device, and through it we transmit the measurement results into the database. So we prepared everything to fetch, meaning to record this data, and today we'll look at how to create a table automatically for our task. In the previous episode, I added a button that we'll use to start the process. Here I had some free space. This is where the fetch button is now on the front panel. And I also added a field here to enter a number. This number will correspond to the different peripheral devices that will connect later. Today we will review and hopefully finish connecting our system. We'll call it Fetch Data 1. And accordingly, our table will be named Fetch 1. And you can see in the background in the lower corner a board with a built-in microprocessor. This microprocessor is called Cortex. It's widely used in NVIDIA devices, and the board itself is called Portenta H7. We will also program it using our application and will receive data from it and write that data into our database, but into a table that we'll call Fetch 2. And for example, we can assign this data stream the name Temperature Control 1. We'll talk about that next time. For now, let's continue with our current topic, creating tables in our database. I'll finish programming here. We'll program the following task. When the fetch button with index 1 is pressed, here's the index 1, a table called Fetch 1 will be created, and we will write the data from our photosensor into it. So last time we created a LabVIEW where we built a virtual object that simulates our system, the photosensor and the USB controller. Now I will open this LabVIEW and run it. As you can see, this LabVIEW records the data from the photosensor. I turn on the flashlight on the sensor, and as you can see, the data is captured. I'll show it again. Yes, the values are being recorded. Let's prepare our LabVIEW for integration. I open the block diagram, and what do we need to add here? First, we need to add error handling messages, and at the same time properly stop our acquisition tool. I will also add error messages to the error line. I finished working on our LabVIEW DAQ fetch 1. This LabVIEW will automatically appear on the screen when I press the fetch button. Let's close this LabVIEW. For now, I won't need it anymore. Now, on the front panel, I want to create an indicator that will represent the start of the fetch acquisition process. For this, I'll copy this boolean and place it onto my fetch button. I'll also make it red when it's activated and rename it. I'll call it fetch start. Why are we doing this? Because when the program launches, our logo should stay in front. It covers all buttons and windows, but when we add new controls, they are automatically placed in front. So we need to remember that and move all new buttons to the back using reorder, move to back. This way, my front panel is ready as well. Now I need to integrate all of this into my program according to the plan I came up with. That means when the fetch button is pressed, my program that collects data from the photo sensor will start, and this data will be written into the database in the fetch1 table. So I have the fetch button. Let's find it on the block diagram. For this button, I created an event case and placed inside the event case structure the terminal of our button as well as the terminal of our index. Here, the number sign or hashtag. Inside this event case, I created a case structure so that when the fetch button is pressed, a pop-up window appears with the following text: fetch data, and next the number 1 will be shown. Then I have two options: activate or cancel. Why do I want to do this? We already adopted the rule that any important operation we perform in our database tool should require additional confirmation from the operator. Why do we do this? There is always a chance that the operator accidentally pressed a button, or sometimes they may not be completely sure what the button does or which operation will be executed. So I placed a two-button dialog and connected our string constants. Here I added the concatenate strings function so that we include the number of the device with which we are performing this action, that is, writing data into the database. If the operator doesn't confirm and selects cancel, we go to the false case, and from there we exit through the enum wait for event into the timeout case. If the operator confirms, we go into the true case. In this case, we check whether the table where we want to write the data already exists. If it does not, we create it. Here we actively use functions from the database connectivity toolkit. Specifically, we use dbtools create table to create the table. We also use the standard functions like dbtools open connection to open the database, list tables to display the existing tables, create table I already mentioned, and dbtools close connection to close the database. Using these four functions, we complete the task of automatically creating the table if it doesn't already exist. In addition, we perform an error check, and if an error occurs, a pop-up error window appears and the operation is stopped. To create the table for our fetch data 1 system, we need 4 columns. I name them as follows. The first column is index ID, the second column is amplitude V, the third column is operator ID, and the fourth column is timestamp ID. As you understand, we could create any number of columns with any additional information, but since we are not tied to any extra conditions, for example, where we are performing the acquisition, for whom we are collecting the data, for what purpose the data will be used, or where it will be sent afterward, these four columns are sufficient for now. And because we initially decided that our database would be stored strictly as string, everything here is defined as string. Why in string format? Because at this stage, we do not want to complicate the programming with additional constraints typically required by standard databases. Here you can also see our other available data types: long, single, double, datetime, binary. But in our case, we use only string. So I define the columns as follows. All columns are string. I set the cell sizes for each column like this. For index ID, 20 characters is enough. For the voltage value in the amplitude V column, I limit it to 2 decimal places. And I also know that the voltage cannot exceed 12 volts. How do I know that? If you haven't seen it yet, check the previous episode. We covered this in detail there. Since the voltage cannot be higher than 12 volts, the total number of characters needed would be about 5. But I gave myself some margin and assigned 10 characters for this column. For operator ID, I also set 10 characters, and for timestamp ID, I assigned 50 characters. I just don't want to calculate everything precisely right now. Of course, when you work with large data streams, you must consider the cell size carefully. This size is fixed, and regardless of how many characters you actually store, the database size will be based on the cell sizes you define. So this is how I configured the parameters for my table, and then I connected our cluster to the create table function. After the create table function, we added a combination of dbTools select data and database variant to data. Why do we need this? I want each record to have its own index, and since the records in our table will continue to grow, I need to know the last record number. To do that, I output the first column, convert it into a numeric value, and find the maximum value. This maximum index value is then passed through a shift register so it can be used in the next cycle. The shift register is located right here. After that, we placed a case structure on the error wire and connected the error line to the case selector. In the error case, we added a pop-up one-button dialog where we provide 3 inputs. First, the string constant dbCreateError. Second, a carriage return constant. Third, the error message using the MGI error message function. We took the error message function from the MGI library, and from the same place we also used the clear error function. The MGI library is located in the menu under error handling, where you can find both error message and clear error. We placed clear error on the error wire inside the error case. Why do we do this? Because if an error remains on the error line, the dbTools close connection function will not execute, and that would mean the database would still be considered open from the user's perspective. Here I should clarify that we are working with the Microsoft MS Access database. We know that if the network is fast, this database can support several hundred users at the same time. Of course, we could leave the database connection open, but in that case, it would be considered that we, as users, are still connected to the database. And if there were, for example, 300 or 400 other users like us who forgot to close their connections, the database might not be able to serve a new user who tries to connect. That's why we always try to close the database properly. To make sure there are no obstacles preventing the dbTools close connection function from executing, we use the clear error function. So, in the error case, we place the enum wait for event. This means that after the error message appears, we transition into the timeout case. Now, What should happen in the no error case? The DB tables indicator window is updated. For this, I added a property node, strings and value, which receives the list of all tables, including the newly created one. Using the dbTools list of tables function, the window will display the name of the table we are currently working with. Next, with the search1d array function, I determine which row contains that table. I also update my DB table. For this, I added a property node, value, and column headers, which will display all records that already exist in that table. And finally, from here, I will control my LabVIEW that works with my microcontroller. For this, I now take the property node from the fetch start boolean, create property node, value signaling, and I place it right here. Then I connect a true constant to it. Now I want to explain this function in more detail. The point is that if we want to control an event structure that is located in another while loop in our program, we must use this operator. The regular value property is not enough. So what will we control using this value signaling property node? We will control a process that runs independently. In other words, we are using the principle of parallelism. What does that mean and why do we use it? If we want two independent processes to run in our program, we need to create two while loops that operate independently from each other. In the first, the main loop, we will handle writing data into the database. In the second loop, we will collect the data. So let's create a second while loop for our sub-program, which is called DAQ fetch1. And following LabVIEW good practice, we will place this while loop below the main while loop. As I mentioned earlier, we will be connecting different instruments, or different systems, if you prefer, to the database. For example, next time we will connect a Cortex microcontroller using the same approach. So in the name of the sub-diagram, we can clearly describe which system this while loop is intended for. I enable visible items, sub-diagram label, and name it fetch data 1. Inside our fetch data while loop, we create an event structure and I immediately set the loop timing to 100 milliseconds so I don't forget later. I also add a power off case so that the power off button works synchronously across both loops. In the timeout case, I place our LabVIEW DAQ fetch1, wrap it inside a case structure, and connect that case structure to our control variables, specifically the global variable stop. I connected the global variable stop through a NOT operator together with fetch start, so they work together. The logic here is as follows. When the global variable stop is in the false state, we change it to true state. And when we press the fetch data button, our property node value signaling is triggered. At that moment, the case switches to the true state. As soon as the global variable stop changes its value again, the case transitions to the false state. In the false state, nothing happens. We simply wait for the next request to collect data. So at this point, we either created the table or confirm that the table already exists. And we verify that there are no errors. After that, we redirect the execution of our program forward. Now we are ready to start writing data from our sensor into the database. We have the operator's request and the prepared table. To continue the programming flow, we need to determine where this task will actually be executed. For this, we use our state machine structure. Inside this structure, we created an additional case and named it fetch data. And this is the final case required for our procedure. So don't worry, just a little more patience and we will see how everything works. So we are now in the fetch data case inside the case structure. Here we also use the database connectivity toolkit in the standard way. We open the database, close the database, and also use list columns, insert data, select data, and database variant data. The principle here is the following. We created the logic so that we open the database, write data into it, and then close the database after the operation is complete. However, since we'll have a continuous stream of data coming in real time, I added a while loop. Here it is. As data arrives through the global variable called fetch1value, we also see the global variable stop, which will become true after the 5-second interval that we previously defined. The same global variable stop will also stop the while loop on our main diagram. We know where the data and the stop command are coming from. What else is important here is that we write our 4 values into the database columns using a cluster. In the first column, we write index ID. As you can see, we increment the initial value by +1, so the index of each record increases by 1. On the second terminal of the cluster, we pass the voltage value from our sensor. This becomes the second column. On the third terminal, we pass operator ID. In this case, our logic is the following. We know that the safe password value is false for an operator and true for an administrator. So we place this on a switch. In this way, in the third column, we record how the user entered the system, as an operator or as an administrator. On the fourth terminal or the fourth column, we write timestamp ID. We already covered how to obtain the timestamp ID in previous episodes. Also, our DB table continuously updates with each new row value. Here I again add on the error wire a property node from the fetch start boolean, property node value signaling. And I create a false constant. Then I move our fetch start boolean into the case variables, change it to an indicator, and create a false constant. And that's it. Our program is ready. Let's run it and see how it works. I log into our program as an admin. And let's say I'm currently working with the inventory table. Now I start the data acquisition, I have my flashlight ready, and I press the Fetch Data button. A pop-up appears with Activate or Cancel. I confirm the operation and press Activate. We can see that the program is running, the data is coming in, and we automatically switch to the Fetch1 table. Are we actually collecting real data or not? I'll move the table down and run the program again. Our program runs for 5 seconds, and to show the voltage change on the sensor, I use my flashlight. Notice that during data acquisition, the red Boolean indicator on the Fetch Data button lights up. Also notice the index sequence. The recording continues starting from the last index value, which was 107 or 106 to be exact, and then increments by 1. Let's go. So, we connected our system that detects light intensity. We convert that light intensity into voltage values and write those changing values into our database in real time. At the same time, the table is created automatically. And let's check how the same operation will work, for example, if I use this as a sensor number 2. For that, I set the index to 2. I move the table down, press Fetch, and here we go. We can see that the table name in the window changed automatically, which means the table was created in real time. So we have completed the real-time acquisition and fetch data into the database. Let me remind you that this database tool program is intended for our portfolio and doesn't have a specific real-world assignment yet. However, by using this logic and structure we created, we can easily adapt it for real applications, for any purpose, any use case, and any task. In the next episode, we will continue working with table creation. As I promised, we will also program the Cortex microcontroller located on the Portenta H7 board using our application. If you're interested, don't miss it. We will also look at creating tables manually using our database tool. And that's all I've got for today. Thank you for joining LaPlante Tech. If you have any questions, please leave them in the comments. If you learned something new today, give this video a like and subscribe to learn more from upcoming episodes.